It's a pleasure to be here, and I echo Martin's comments. I think it's really nice to be in this new venue. We go to a lot of meetings, and I think many of those meetings talk about the same things over and over. And I think what Max and the team here has done is created something new. And that's really exciting because we need new solutions to Alzheimer's disease. And we're not going to get there doing the same things we've done that, as Martin pointed out, have not really worked. And so with that, I'm just going to start off with a little question. I have a disclaimer. And who here has heard of Biohaven? Can we raise our hands if we have? Okay, so Biohaven is a group of folks. We're all neuroscientists. And many of us come from Bristol Myers Squibb, which is one of the companies that no longer does neuroscience. And if you Google Biohaven, you hear a lot about our CGRP platform, our migraine drug, which has had some really exciting positive phase 3 data. But you don't necessarily hear a lot about our glutamate platform, which is what I'm going to talk to you today about. The folks at Biohaven, including our Chief Medical Officer and Chief Scientific Officer and CEO, have been studying glutamate for quite a long time since they were faculty at Yale. And we are studying the role of glutamate in quite a few different disorders, neurologic and psychiatric diseases, including Alzheimer's disease, in late-stage studies. So also, my next question for you is, who knows what glutamate is? Do we have a student in the room? Okay, we can see the students up in the back. Can someone tell us what is glutamate? Exactly. So glutamate is essentially the most important excitatory neurotransmitter that we have in the brain, and it's present in about 90% of the excitatory synapses in the brain. And so it's not surprising that glutamate dysfunction is relevant across a broad range of disorders, including neurologic disease and psychiatric disease. And in fact, it's one of the validated targets for treating neurodegeneration. In ALS, excitotoxicity has been treated with Troriluzole, which is a medicine that targets glutamate and reduces it at the synapse. And I'll tell you a little bit more about that. So you can see here that glutamate transporters, the glutamate receptor, are two different potential targets for glutamate modulating medicine. And at Biohaven, we have both. And here's a cartoon that really shows the two targets. So here is the glutamate transporter, which is on the glial cell. And here is the glutamate receptor, or NMDA receptor, which is on the postsynaptic neuron. And these little red dots are all the glutamate. When you have too much glutamate, you get overexcited at the neuronal level, and it often can lead to cell death, particularly of the neuron. And we have many treatments that potentially have tried to target the NMDA receptor. And in fact, it's a validated mechanism for treating the symptom of Alzheimer's disease. So memantine is a drug that targets the NMDA receptor, and it shows that it improves symptoms of Alzheimer's disease. So I think it's important to note that in Alzheimer's disease, and more generally across neurologic diseases, we often look for something totally brand new. Here we have something that sort of works. Okay, let's find something totally new and start from scratch. Rather than taking what we have, what we know works, and trying to improve it. This is something that I think is really in distinction to our cardiovascular and our oncology colleagues, who often take a stepwise approach and start with one thing. If it works, then they make it better, then they make it better, and then they make it better. And so that is in part what we have done with Troriluzole, which is the drug I mentioned, which is a drug that treats neurodegeneration and Lou Gehrig's disease, or ALS. And we've created a prodrug, a drug with much better pharmaceutical properties, and that's called Troriluzole. And that's this drug that we are studying in Alzheimer's disease. So why we started with this drug in Troriluzole and tried to make it better. We know that the drug has been around since 1995, so it's been used. We know its safety profile. There are potentially studies that have been showing that in the modern day, when you treat people with ALS and you do everything else, that this can prolong survival by up to 21 months. So the initial study showed maybe 3 to 6 months, but in the modern day, this seems to work because we treat patients more aggressively for their other things like their respiratory problems that you find in ALS. And so we think that this has really potential benefit in ALS, but there are limitations. It requires daily dosing twice a day, and you have to fast around the dose because it's not absorbed with food. And so that's a significant problem. Who here doesn't want to eat for 6 hours a day? And if you do, then the drug that you're taking doesn't work as well as it's supposed to. The liver is very sensitive to Troriluzole, and so at certain doses, above the 100 milligram dose, you can't give the Troriluzole, and because it causes liver issues. There's a lot of variability in the drug itself, so just the metabolism of the drug can give you a lot of variability. So when the drug levels, you don't really know what they are, you're not achieving the right drug level, it's hard to know that the drug works, but even in that context for ALS, it does seem to work. So what have we done? We've worked with medicinal chemists to make the drug better. The absorption is better, it's more bioavailable, the burden of the drug because it's directly absorbed is much less. It doesn't go through the liver because it's directly absorbed from the GI system. It has a much better safety profile and can be dosed once a day. So we think that these are really advancements over the existing drug. And part of the reason for that is that the prodrug targets this peptide transporter. The prodrug is directly absorbed into the GI, from the GI system into the bloodstream through this transporter. That's why it has those properties that I mentioned. So let's shift gears down and talk about Alzheimer's disease. We all know this, we've been talking about this all day. The hallmarks of Alzheimer's disease are things like brain atrophy or brain shrinkage, neuronal cell death, amyloid and tau, and the loss of synapses. This is the thing that's actually the most correlated with the disease symptoms. And largely these are glutamate synapses. There's another thing which sometimes gets lost, which is glial cell dysfunction. So the glial cells, which comprise 80% of the brain, as opposed to the neurons, are also dysfunctional. That's not a surprise, but we don't have a lot of things that target the glial cells. So one of the hallmarks of the glial cell dysfunction is something called GFAP expression. This is expressed in a lot of glial cells, and you start to see that the phenotype of these can be protective early on in a disease like Alzheimer's disease, and perhaps later on you get the amyloid and the brain atrophy, because these support cells are doing what they're supposed to do early on. They're trying to support those dying neurons or sick neurons before the disease manifests. And when the disease is actually there, you can measure these. These are seen on autopsy. And one of those things that is a hallmark of those glial cells that are not behaving well is GLT1 or glutamate transporter levels being reduced. And this is associated with impairment of the synapse. Here are some brain slices where we're looking at that glutamate transporter. And you can see the healthy controls. You see a lot of green. And this side on the right side, in the Alzheimer's disease patient, you don't see those. And so we think the GLT1 transporter, which is the target of Troriluzole, is a very interesting potential therapeutic. And when you look at the properties of the glutamate transporter in Alzheimer's disease. In animal models, if you modulate the glutamate transporter, that really has a big impact on the symptoms. So if you use genetic approaches or pharmacological approaches. And so, again, these are some of the preclinical data that highlight this target, the glutamate transporter on the glial cells, the 80% of cells that we usually don't target. Here's just a little bit more of the rationale that we have for studying troriluzole. So the active metabolite, troriluzole, increases GLT1. It rescues symptoms of Alzheimer's disease. So this is in the animal model, improves thinking and memory. It also reduces some of the pathological features, things like amyloid and tau levels. We know that glutamate modulation is a validated target. And so we think this is a really interesting agent, troriluzole, to treat Alzheimer's because it can potentially target symptoms as well as the disease pathology. I'm not going to dwell on the science here, but there is very good science across animal models, including amyloid, tau, aging, in vivo animals, in vitro cell and synaptic function models that shows the potential benefits of troriluzole in Alzheimer's disease. This is as good as any other drug out there that's been in development. And in fact, now we have some interesting data from that's not even on this slide. It sort of keeps increasing. And why is that? If troriluzole has been around for quite a long time, it's because some of the interest in Alzheimer's disease is very recent, and it's driven by new tools and techniques, whether that's animal models, like very aggressive genetic animal models of AD, or also just some of the techniques, so single molecule sequencing of genes and proteins, etc., in animal models. So this is very current work, and we're really capitalizing, well positioned to capitalize on it. And this is a summary of what we think the value proposition for studying troriluzole in Alzheimer's disease is. We think that we can target all of the hallmarks of Alzheimer's disease, including the symptoms and the pathology and the pathophysiology. And in fact, this is by targeting the validated target of glutamate, and it has the potential to improve the symptoms and to improve potentially the disease pathology. The study that we're currently running is a phase 2-3 study in Alzheimer's disease, mild to moderate patients with a standard type of design. And we really hope that this study will give us some interesting signal that we can follow up on for efficacy in the mild to moderate patients to treat the symptoms. We're doing this in collaboration with the ADCS, the Alzheimer's Disease Cooperative Study, and we plan to have a futility analysis at the end of this year so that we can be quite efficient in terms of our study. And we look forward to sharing those results and this total study results in the future. Thank you.